Hello, this is Paul Gregg. I wasn't going to I recently installed a Zipline and did the calculations for it, and I didn't think it was worth, it's been well treated over lots of the internet, YouTube videos and whatnot. But yeah, I'm going to make a little engineering video about my Zipline because there's some things I discovered, and there's a lot of different, there's different viewpoints on this, and discovered a few things. And so, starting out, um, I went to this. I have a bunch. I tried it with a bunch of different websites and came up with different answers on most of them. So, but this one called Zipline Gear seemed to be pretty good. Pretty good place to start. Um, um, so, as I went through. I looked at you come on. There's terminology. You have a one tree and a different tree, and then you have a low point. Um, and it talks a lot. This is a very good information about what you should use for an anchor and what you shouldn't use. And clearance is how uh, the entirety of the zip line, how much the line, how close it is to the ground. Then there's cable slope and sag, and they kind of have a recommendation for what percent. This is very interesting. The zip line must never exceed 6%, 6% drop. So if it's 100 feet long, it shouldn't drop more than 6 feet from one tree to the other tree, shouldn't be more than 6 feet. Now, that's when I bought my kit, I opened up the instruction stuff and they said 8% maximum. So there's a lot of variation on this. Sag is how much it is okay, here's you determine your length, and mine was 118 feet, and so I bought a 125-foot kit. The zip line slope is how much you're going to drop from one to the other, and you have to account for how much my slope dropped 2 feet, so you have to kind of account for that. But this is the actual slope on horizontal, and then the sag is how much it's going to sag when you're riding it, and they suggest the sag be somewhere around 2% of the length. So they're saying the zip line slope should be 3 to 6%. Um, and then you just have this little you fill this out, and it that was a good starting point. So then I went and did that. They recommend a sag is the so this is a picture. I got one tree here and another tree down here, and my ground dropped 2 feet. Okay. So I put it in a spreadsheet because I knew I was going to recalculate it a bunch of times. So that's what's good about a spreadsheet is you can recalculate things pretty easily, and you can be fairly sure you didn't make a mistake. The bad thing about a spreadsheet is it's hard to show the equations I'm really using, and so there's those are treated other places. You can get really good YouTube videos or websites that have good graphics and everything like that. So I'm just going to go over a few things that I learned and a few discrepancies between the different companies or engineers that have done this. Uh, uh, so SAG 2% of the length. So 2% of 118 is 2.36 feet. And I'm just operating in feet. I switch to inches when I really have to measure something, but we're just going to stay in feet for this. Drop, I went about the middle of what they recommended, 4.5%. But like I said, my kit came and said you can go up to 8%, which means it's just faster, probably. But it's a trade, Yeah, you can slope it more and it can go faster, but at the end you have to slow down and stop. And if you're going faster, especially at the end, you can really hurt yourself. You can look up zip line fails on YouTube, and there's people running into trees and getting hurt and everything like that. So my length 118, like I said, then this line that goes from the top starting point to the ending point, that drop is called the length, and so the drop divided by the length is the percentage uh, of drop. Um, Clearance, I tried to keep. I started out with 6, 7 feet, but then I'm mostly riding little kids, and so I went to 6 feet. I'll I'll cover that later. The sag 2.38. So the height at the end, at the first start was height at the second end was 8.36 feet because you add account for the 2 feet there, and the height at the beginning was almost 12 feet, and that that didn't seem too bad. I might build a platform here, but generally I put the rider on and then I have a rope on it and pull it back. And so then they're on the seat and they're holding on the whole time. They aren't trying to get up on a platform, trying to get climbing up on a platform. So I think that's a little safer. Um, so now that's the calculation I found online that I thought was pretty good at Zipline. So then the one I bought is CTSC. It's on Amazon. I'll show it to you. So this is the one I bought on Amazon. It seemed to be a good price, and it included a little more than other ones did. So this is the one I bought. It's I only go on 125 feet. I'm not riding real heavy people, and so I went with the this one here, $150. It comes with a 3/16 cable. The difference between that and the longer and ones that carry more people is the diameter of the cable. And I'll talk about the cables that you're buying and one interesting thing about that, they don't, you're really using these cables at a higher load than the manufacturers recommend. And I didn't see anywhere that wasn't using them at a higher load than the manufacturer of the cable recommended, which is an interesting thing I'll talk about at the end. So this is the one I got. The nice thing about it is it comes with lots of stuff, some tree protectors, and this ratchet strap is just so you can hold it while you're tensioning the line, and that turned out to be a really good addition. And then you end up it's just a tie down strap, and if you don't have to have this, but it really helps to have a come along or a tie down strap, ratchet some kind of ratchet strap to when you're putting it up. And I can see trying to do it without that would be a big pain. It does come with a harness in case you have a kid you don't trust very well, and they're kind of, and so I will probably not use that very much. But the nice thing is this trolley is all metal. Bearings are metal, the sides are metal, and so that seemed really good. This is the seat's plastic, but that could be stainless steel spring brake over 6 feet, which seemed really nice. Seemed like a pretty decent quality carabiner. There's the cable and the sling cable and the turnbuckle, which you use to do the final tensioning at the top end, uh, and then a bunch of just so the hardware seemed okay for $125. I can't believe it. Seemed really good. Now the more expensive one is one with a thicker spring, and I'm having it to do over. Maybe I would do that because maybe, but I don't plan on. So here's down at the bottom here is a comparison of different ones you can buy, and here's some nice pictures about and you got to decide who's going to write it. So so you can see the cheaper ones are shorter and they're up good for 250 pounds, and the more expensive one is has a thicker, goes from 3/16 or 5 millimeter to a quarter inch, a 6 millimeter cable, and that they're saying that's good for 350 pounds, which is good, and it's 205 feet long. So you got to measure between your trees and or your anchor points and make a decision on that. So back to my spreadsheet. This is the calculation here. Uh, this is what the manufacturer of my zip line said. This is my length, uh, and they wanted an 8% drop. And so, of course, that means that the starting point's higher, and uh, and that's how much it would drop over 118 feet, which would be really, it's faster. But what happens is if you get really fast at the front end, and you're gonna always going to have sag, and then you're going really fast here. If you're going too fast, when you start to go uphill at the end, okay, and that slows you down, and then you hit the spring, and how violently you hit the spring is depends on how much speed you got in the middle of it. And there's a happy medium there. And if you're riding teenagers and maybe they want to go faster, but if I'm going to ride little kids and I don't want to go that fast, and so I kind of put a compromise out, and then I settled on 4.5% drop or something like that, kind of in the middle. And that's where I went with. And then as things go, when you finally build it, it's a little different. So the height on the starting end, 12.5 feet, the height on the other end, 8.5 feet, and so my drop is 6 feet because I have 2 feet of drop natural to the ground. That's a drop of just over 5%, and my clearance was a little over 6 feet, and I'm happy with that. And we tried it a few times, and I'll show you that. So, from an engineering standpoint, this is what they tell you, and when you buy it and do it, there's two kinds of engineers. Well, lots of kinds of engineers. Uh, some engineers go to college and they learn how to do stress analysis and deflection analysis, and that's really great, and that's what I did. And so I'm interested in the analytical side of engineering, but there's the design side of engineering where you could just go out and put up zip lines and try them, and you put up 10 zip lines and modify it and come out with really what you want. And you could do that analytically um, uh, before and just put it up once, or you could do it 10 or 20 times with different cable sizes. If you start too small, you're going to probably break a cable or something. And and if but if it's not going to kill somebody, maybe it'll or injure somebody seriously, then and well, I've done a lot of videos about my backyard roller coasters, and in the late 1900s, or even earlier than that, when roller coasters started, it was just clever people who would go make one and try it, and they had roller coasters that almost killed people or did kill people, and they were always trying to get more exciting, but they were doing it in an experimental way. So they build a roller coaster and then they would let people ride it for a while and find out people's necks hurt. And so that roller coaster would go away and they build another one. So that's a really expensive way when you're doing a roller coaster or an airplane or a building or anything or a bridge. Empirical, which means I tested it and I just keep iterating between building and testing. And if you're in empirical engineering, um, you can end up with a great answer, but getting there, you could hurt a lot of people, and so the analytical side, and I think the best thing is a crossover between analysis and design, and whatever you design and test, you analyze that, and then that helps you come around in the iteration to come to a better design. And so the math and the analysis can really help you. You can do it without it, but somebody might get hurt, and you might spend a lot of money making things. Now, in a zip line, it's not a lot of money, and so that kind of goes away. And so the empirical, you can get by with doing empirical things. And it's a difference between what I would say is an engineer and a maker. Makers, they just build it and test it, build it and test it. And that's one way to do it. And it turns out really well. The analytical side, you design it, analyze it, and then design it again based on your analysis, and then you build and test. And so if building and testing is very expensive, that's really a key component to it. Now you can get people who went to college and don't have much common sense about what they're doing. And they don't have any experience. So, I've never made a zip line before, and so I just started. And they can make mistakes too, because analysis is a model of reality. And the better your analysis, yes. But is your analysis good? Is the analysis been calibrated to a real test or real life? And so analysis needs some iteration too to make sure it's accurate. And there's a lot of variables even in a zip line, and it's hard for analysis to account for that until they experience it and then to modify the analysis. So um, everything has limitations, but I think a combination of both design and analysis uh, in conjunction with building and testing is really the way to go. So, uh, in the end here, I wanted to know how much stress is in my cable. So this is kind of the engineering side of it. So in order to find out how much, what you want to do is I'm putting a 250 pound weight on this, and in a deflected position, there's reaction one and reaction two. That's how much load there is in in the cable. Okay. When I put a 250 pound weight on there. And then to do that, you have to know what the angle is here and what the angle is over here. And um, so this is I determine the angles from CAD. I have a CAD program, and you could do this mathematically with simple trigonometry, but it was easy enough to just look at my model and put these angles in. So you're going to use sine and cosine. So here, what you do is you draw a free body diagram of that point right there. And what you get is this. And then what you know is that the forces in the y direction have to equal zero. When you sum them all together, and the because it's a static condition, it's not moving. You also know that in blue here, the sum of the forces in the x direction, they also equal zero. And so you have two unknowns. You don't know what R1 and R2 is. Okay. And R1 and R2 are broken down into X and Y components. And this is a common thing in engineering. So that R2 has a direction, it's a vector, and it has a magnitude. But it can be divided into the Y portion of that and the X portion of that. And so this is R2 in the X direction, and this is R2 in the Y direction. Okay. And so once you know that, you can sum the forces in the y direction, you can sum the forces in the x direction, and what you get is R1 in the y direction plus R2 in the y direction. They're going up, they equal 250 pounds. That's what you know. You can make this equation. What you also know about in the horizontal direction, you know that R1x equals R2x, R2 in the x direction. Okay, so you have two equations and two unknowns, and that's kind of magic for uh, for an engineer is because when you have two equations and two unknowns, or four equations and four unknowns, I can find out what the things are. Um, so you solve for, let's say you solve for R2 here, and you have to do this in terms of the angles, and then you just plug it into this one, and then uh, you can solve for the other variable. And then once you're done that, you can go back and look at the first variable, and you know what they are. So this is what I did. And this is R1, 2,037 pounds. And this is R2. They're pretty equal. If this was in the middle, obviously, they would be equal, but they're fairly close to equal. Now, what engineers do is say, all right, I looked online and this cable breaking strength, this is the load at which the cable will snap. And that's determined by test. 3,800 pounds, and I'm putting over 2,000 pounds in this cable. And that's a little, well, I'll talk about why that may be a little risky, but it's not really risky. But so engineers have what they call a factor of safety. So even though my loads are my limit load is 2,000 pounds, my ultimate load, which I want to design to, is 3,000 pounds. And then we do another little formula. Uh, I can take 3,800 pounds. I'm going to load it to my ultimate load is 3,000 pounds. And so I do a one minus the stress divided by the strength. And that gives me a strength margin of 0.942. And as long as that number is positive, then my design is good. And it also gives me an indication of how much over designed it is. Okay, if this was negative, then I would know I had exceeded my strength, and I could predict it was going to break. So there is a factor of safety in there. It's just a manipulation of numbers, really. But I know this is a good design. Here's what's interesting, though. If you go online and say, I got a 3/16 galvanized steel cable, what's the strength of it? And they'll say, yeah, the strength is 3,800 pounds, but the safe working load, and every one of them will tell you this, is 740 pounds. And you think, wait a minute, I'm putting 2,000 pounds in this cable, and they're telling me the safe working load is only 740 pounds. So what am I doing? And every backyard zip line is the same way. You're going way beyond what the manufacturer of the cable calls a safe working load. And so I did a little calculation of the stress and came up with 74,000 pounds per square inch is the stress. And that's, well, you go online and look, but I didn't do that. So I've switched to metric units, megapascals, which is a Newton per meter squared. Okay. And because meters are so big, these numbers get really big too. Then you call it a megapascal. And mainly did that because I found this nice chart online that says this is the stress strain curve. Um, and if you look at the stress strain curve, so stress is the load per unit area. So this is how much load it can take per unit area. Okay, it's in pounds per square inch or megapascals, which is a Newton per meter squared. Meganewton per meter squared. Okay, that's the stress. And when you do a tension test, you pull on it like this, you're recording two things. You're recording the force that it's exerting, and you're also recording the stretch or the strain. Strain is just the stretch divided by the original length. Okay, and so this is a very important. Every material has this, and this is what really engineers look at when they're assessing materials because let's just talk about the stress strain curve for a little bit, okay? So you stress it and you pull and then you go back and you pull and you go back and you pull and you go back. So what you see here is that it goes back to zero, okay? If unless you stretch it, unless you apply too much load, it goes out here and then it doesn't go back to zero. So whatever goes back to zero, we call that elastic strain, okay? And whatever doesn't, if you go higher than that and it goes back to not zero, then we call that plastic strain or permanent deformation, okay? And those terms, if you're going to be an engineer, a mechanical engineer or civil engineer, you get very familiar with that kind of thing. I found this chart, and so I switched to um, metric units. Uh, so my stress is 510 megapascals. And you can see if you go up to 510, we're way in the elastic limit here, so we don't have to worry too much about it. But so way down here is what the manufacturer suggests that you never go above. And so there, and you're going to manufacture cable, you're not going to want to get sued. And plus cable can get damaged, a few strands break loose, it gets old, it gets stepped on, it gets all kinds of things like that. So the manufacturer, the reason they say the safe working load is 740 pounds is because sometimes, a person's life depends on this cable, and they're going to have an extra factor of safety in for that. You don't know how old the cable is, if it's had chemicals on it, or if it's been stepped on, or if it's been hit and has some fibers broken or whatever. So they're very conservative when they say the safe working load is 740 pounds. They don't want to be up here taking any risk at all. And so they really back off on how much these cables can do. And um, you also don't want to go, you can imagine, and I think this happens if you really if you really put a lot of tension in your zipline cable, and then you have heavy people ride it a bunch of times, you probably go plastic and you're out here somewhere and then you come back. And that's why people own zip lines, if they're really using them, heavy people and everything, they'll say, well, now it's sagging more than it used to. And what happens is this length has gotten longer. The deformed length has gotten longer because you went plastic. You went past the elastic limit, uh, past the yield stress. It yielded, and then this is a nice thing about a lot of metals is that you can go past the strength, the yield strength, but it doesn't let go. Okay, it starts to stretch, but it actually gets stronger by work hardening. Okay, and work hardened materials are stronger, but all they've been doing is they've been stretched a bit, and so they have a higher strength. It looks like they do have a higher strength. Um, so that's what work hardening is, and that's a very simplified explanation of that, and you can get a lot more better information than that. Um, so I found this chart, um, and we're working down here. This is how much capability you have, so you feel pretty good about it, even though you're going past the manufacturer's recommended safe working load. And I think, like I said, all backyard zip lines do this. They go past this. Otherwise, it would be a lot more expensive, and it would be, I guess, over designed if you went to a 3/8 inch cable or something. It certainly would be safer, but it would be a lot more expensive. And this seems to work. One last thing, it's very interesting. I decided to calculate how much elastic stretch this has. We know that this path is longer than this path, and this is 118 feet. So how much longer is it? Interestingly enough, if you just go by this and you say, look, if I'm stressing it to 500 megapascals, I can get over nearly uh, 0.5% of strain in it, and that ends up being 6 or 7 inches. And you think about that, you think, so every time I use my zip line, I'm stretching that 118-foot cable. I'm stretching it 7 inches. And that's really what's happening. But it's elastic, so it goes back. It's like a big rubber band. And all materials are somewhat like a rubber band. It's just that they're a lot stiffer, and so the stretch is a lot smaller than a rubber band. I went to an online calculator and came up with this is for cable, for a stainless steel cable, a little bit different material. And they were almost 10 inches stretch. And I think what that has to do with is the cable itself has a bunch of strands that are woven and go together. So there's some stretching just due to the geometry of a cable. And then there's stretching due to the material of the cable. And that's why that number's bigger. But that's very interesting. You can have 118 foot long zip line, and you're actually stretching the cable seven 7 inches every time you use it. I thought that was a very interesting thing, but it makes sense. The geometry kind of shows you that this path is longer than that path, and this is 118 feet. And yeah, it's not hard to imagine that that's 6 or 7 inches of stretch. So we're this is this is our testing. Put it between these two trees. This is my wife. She's my test pilot. I won't tell you. She wouldn't tell me how much she weighs, but that's it. You can see I have a rope on there, and I just pull the rider up so they don't have to be transferring from a platform to the little seat. Okay. So that's not the definitive engineering explanation of zip lines, but that's what I did, and I documented it.